We have to get 2 of the first 4 have to be defective. So what's the first probability you want to write down?
4 over 15.
Okay, so that represents getting a defective one as the first one, right? Okay, then the next one?
3 over 15.
Okay, so you're saying we get a second defective one, right? There are 3 defectives left and 14 total players left, so chance we get a defective again is 3 over 14. Okay, then we have to get a not defective one next. What's the chance of that happening?
11.
Out of
13.
13. And then you have to get another non-defective one. Chance of that would be 10 out of 12. Okay, now with this method, what we just found was the chance that it goes defective, defective, not defective, not defective, right? That's what we applied by multiplying those fractions together. Because notice, if we did it, let's say we did it the other way, first 2 are not, and second 2 are, then the first probability would have been 11 over 15, right? Followed by 10 over 14. Then we would have gotten a defective one, which would have been 3 out of 13. And then another defective one, which would have been 2 out of 12. Those 4 fractions are not the same as these 4 fractions. But do you see the product of these 4 fractions is the same as the product of these 4? Because you're multiplying 4, 3, 11, and 10 on the top. Oh,
I think it did
4 and 3, not 3 and 2, right? These should be, you should be getting the same answer here. 4 here and 3 here. So 11, 10, 4, and 3 on the top, 15, 14, 13, and 12 on the bottom. So even though you have 4 different fractions here and here, the product of these is the same as the product of those, which makes sense because the chance that the 2 defectives are first shouldn't be any more or less likely than the chance that the 2 defectives you end up with are the last 2 you picked, right? So the probability of it happening in that order and the probability of it happening in that order are the same, but both of these should be included in this probability because this doesn't specify when you get the defectives, only that you get 2 defectives and 2 not defectives, right? So, and there's not only these 2 orders, there are more orders than that, right? That all the orders are equally likely, so you don't have to write this out for however many times there are. You can write it out once if you can just then figure out how many orders are there. So what we really need is to know how many ways could I rearrange this string of letters, right? D, D, N, N. How many ways can I rearrange that look different? So we already have D, D, N, N, and this was N, N, D, D, right? What other ones are there? DN, DN, and the reverse of that, right? Are there any others? DNND, and the reverse of that, and DDN. Are there any others? That's it, actually. Okay, that's all there are. So the number that should go in front of here then is 6. Okay? Now, you don't have to write them all out every time. If you like this way, there is a way to calculate this. Can you, 4 choose 2 is one way to think of it, okay? Can you rationalize why doing 4 choose 2 gets us what we want there?
Because if you're choosing 2 out of 4,
What are you choosing?
the D's slash N's. I forgot what these stand. The defectives.
Okay, so what, but usually this is like, this is how many things you have to pick from, and this is how many you're going to pick, right? So there is a way to like connect that to this operation here. The way that I would think of it is, think of it as you're filling slots, right, with D's and N's. You have 4 slots, and you have to pick 2 of the slots for where the D's go. But once you put the D's in place, the N's automatically go in the other places. So you don't have any free, like once you've chosen the D spots, then the N spots are determined, right? So, and you're going to choose 2 of the spots because you want 2 of those slots to be filled with D's, right? So you have 4 slots, you're going to pick 2 of them to be the D slots, and then once you pick the D slots, the N slots get filled in automatically. So that would be a way to say, we have 4 slots to choose from, I'm going to choose 2, the 2 I choose are where the D's go, and then the N's go in the other places. Or the other way around would be the same thing, right? Okay? So that is one way to think of it, and that works for this. That will work if you only have 2 options for what to put, because you're going to choose a certain number of them to be one kind, and then the other kind has to automatically go in the rest of the slots, right? Now, sometimes we'll have problems where there's not just two categories. I'm going to show you an example in a second where we're picking marbles out of a jar, but there's 3 different colors of marbles, okay? So sometimes your arrangement of letters here might not be limited to just 2 different letters. So there's another way to calculate this 6 that turns out to be the same. Do you remember the formula for this is 4 factorial over, what's the rest of it? If it's 4, choose 2. 2 factorial for this, and then the other one is actually the difference of these, so that would be, in this case, a second 2 factorial, right? Okay, there's another way to think of this in terms of how many ways can you rearrange this, which is you start with how many things are there to rearrange. There's 4 things. So if these things were all different, there would be 4 factorial ways of arranging them, right? But in this case, there should be less, because if you just rearrange the D's or just rearrange the N's, it's not going to look different, right? This 4 factorial, 24, we only got 6 different ways. You could think of it as there are actually 24 different ways, but the other ones don't show up because they involve switching the N's and or switching the D's. And if that's all you do, it's not going to look different than it is right now. So what you do is you start with the factorial that represents how many total things you have, but then you divide by how many ways are there to just rearrange the things that look the same. And we're dividing by those because we want to like count all of the rearrangements of the identical things as one result, not a whole bunch of results. So we should have a 2 factorial here for how many ways are there to rearrange the 2 D's, and another 2 factorial here for how many ways are there to rearrange the 2 N's. Okay? And that turns out to be mathematically the same as doing 4 choose 2, so either way you're going to get a 6 here. Okay? Does that make sense?
Yeah.
Now, if this is driving you crazy about having to figure out all this, that's why I showed you there is another way to do this problem that doesn't rely on you having to figure out the orders, right? We could just do one fraction here where we're counting up on the bottom what's the total number of things that can happen, and on the top what's the total number of ways that what we want to happen can happen, right? And you can do that with the choose notation. Is that what you did, Ryan?
Yeah.
Okay, so what goes on the bottom? What's the denominator?
15 choose 4.
15 choose 4. That's how many different ways you can pick 4 DVD players, right? But on the top, we have to have, if what we want to happen happens, we get 2 defective and 2 non-defective. So we need to count how many ways are there to do that. How many ways are there to pick 2 defectives? 4 choose 2, right? This problem is brought to you by the expression 4 choose 2. Okay? Gets lots of free advertising here. But you can't just leave it like this because you're picking 4 and you've only picked 2 here, and you can't just say whatever happens to the rest, who cares, because the other 2 you pick have to be not defective, right? So how many ways are there to pick 2 more where we're sure the other 2 we pick are not defective? 11 choose 2. Okay. I should have done this first. Shreyans, I know you multiplied all this together. If you multiply that answer by 6, what was the decimal version of that?
0.241.
So 242 it would be to
Yeah.
like rounded. 3/6 answer would be 242. 0.242.
What
Okay.
happens if you do 1 3 6 3?
If you do more, as long as the answer you write rounds correctly to the 3/6 answer, you're fine. So if you wrote 241, what was it, 2417 or something? If you wrote 2417, they'd be fine with that. But if you messed up and you wrote 2413, which would not round to the 3/6 answer correctly, then that would be wrong.
What if you wrote like 2 4 2 7?
No, because that would round to 243, right? Yeah. So you can, you can copy down more of what's in the calculator than just the 3/6, but if you copy down more, you have to make, like, they're only going to take off if what you write that's more rounds to 3/6, not to the answer they're looking for. Then you would lose the point. Okay? All right, so this way we should get the same 0.242. 4 choose 2 we already know is 6. 11 choose 2 is going to just be 11 times 10 over 2, that's 55. And then 15 choose 4, does somebody have that? I think it's 495, but I don't exactly trust my memory.
It's 1,365.
Oh, 1365? 495 must be another thing we're coming up on. 15 choose 4 is 1365?
Yeah.
Okay. And this is 330. So is 330 over 1365 that same 242 number?
Yeah.
Okay. All right, is everybody okay with this problem, one way or the other? Okay, all right. I did put a slide in here to go over this idea. If you like this way, and you want an easy formula for calculating this, I'm showing it with the, like, how many ways can you rearrange a string of letters where you've got some repeats, okay? So I did this, okay? If you're rearranging letters in a string, it would be just count up how many things are in the string and that factorial, except that only works when all the things are different. So like that works for the word bad, all three things are different. So this is just gonna be 3 factorial, which is 6, right? But in good, you would start with 4 factorial, but that overcounts because any arrangement where all you do is switch the two O's, which look the same, is not gonna count as, it's not gonna look like a different result, so it shouldn't count as a different result. So we have to divide this by the number of ways that you can rearrange the two O's, which would just be 2 factorial. So this answer is not 24, which is 4 factorial. It's 24 over 2, which is 12. There's 12 different ways to rearrange them. Okay? And then if you take the last word indifferent, which has a lot of letters, 2, 4, 6, 8, 10, 11 letters, right? So if they were all different, this would be 11 factorial, which is huge. But it's not actually that many because there's a lot of repeats there, right? So anything that repeats, you want a factorial expression that represents how many ways can you rearrange just the stuff that repeats. So here I have 2 i's, which can be arranged in 2 factorial ways. But I've got some more repetition, right? What else? 2 f's, so that's another 2 factorial. You say 2 n's, yeah? 2 e's. All right, that is 8 letters. I think I have 3 different letters besides those 8, right? I have 1 D, 1 R, and 1 T. So that accounts for all the letters. So instead of 11 factorial, this is going to be 2, 4, 8, 16. 11 factorial over 16. Which is still a huge number, but not as big as 11 factorial. Okay? You might have seen this before in Ivy Creek Cal, but I wouldn't be surprised if you forgot it because it's not like you're doing this on a daily basis. Right? I remember when I taught Ivy Creek Cal, we did a couple examples of this with some state names, right? Like Tennessee and Mississippi are good ones for this. Right? So Tennessee has 2, 4, 6, 8, 9 letters in it. And if they were all different, 9 factorial is how many ways you could rearrange that. But this is way less than that because what can I put on the bottom here? There are 4 e's, so just rearranging the e's by itself, that's 24 different results that should all count as one result, right? Because it won't look, if all you do is mix around the e's, and there are 24 ways to do that, any of those arrangements is going to look the same as this one does, right? And that's not all. What else goes down here? 2 n's, so 2 factorial for that. 2 s's, right? So it's 9 factorial over, this is 24 times 2, 48 times another 2, 96. 9 factorial over 96. Okay. Make sense? Okay, so if you like the multiply fractions way instead of the combinations way, that is a way of quickly calculating like what's the number that goes in front of the fractions that counts how many orders. Just write down a representation in terms of a string of letters for like what the order is that you found, and then use that formula to see how many other arrangements would there be. And that number goes in front of the fractions. And then you get the same answer as if you did it the combinations way. Okay? Okay. We're gonna do another example here and I'm gonna do this in 2 different scenarios to show another issue that comes up sometimes in the context of a problem. So we have a jar here that has a bunch of marbles in it, 12 altogether. 3 are red, 7 are white, 2 are black. We're gonna pick 4 marbles, but the first scenario says we're picking them with replacement. Now that is different from the DVD example or from the example I did on Monday where we said without replacement. If you're picking with replacement, what impact does that have on the problem? What's that? You're picking from the same amount, so the probability of getting like a red marble, initially the probability of getting a red marble is what? What's the chance that I pick a red marble out of this jar? 3/12, 1/4, okay? Because I'm putting it back, the chance I pick a red marble on the first selection is the same as the chance I pick a marble on the second or third or fourth selection, right? Because every time you pick a marble, you're like recording what it was, then you're putting it back, so all the probabilities are gonna stay the same every time. So this is an example where like event A, the selection of the first marble, and event B, the selection of the second marble, those are independent events now, right? Because whatever happens on the first event, whatever kind of marble I get, the probabilities for the second event of each of these marbles is going to be the same as what they were for the first event, because you're putting things back the way they were before you make your second selection. Okay? So when you see this is independent events. And that is not what was happening with the DVD players or the examples we did on Monday, where we weren't putting things back. That's dependent events. Okay? All right. Another important thing is, if you have this with replacement idea, and you're doing these kind of problems that are kind of like what we just did on the warm-up, when you have replacement, the choose option is not available to you. Like, we have to multiply probabilities together this time. Do you see why? When you do choose, like if I want to say, how many ways are there to pick a red marble, or how many ways are there to pick 2 red marbles? 3 choose 2. 3 choose 2 presumes what about the situation that is not the case here? What could happen in the actual situation that is not going to be accounted for if I just count this as 3 choose 2? Francis?
You can choose all red.
Well, okay. I mean, like if I'm picking, I mean that is true that could happen. But I'm thinking like when I pick 2 red marbles, like what's the chance that I pick 2 red marbles? If I do 3 choose 2, there are certain outcomes that are counted. But there are other things that could happen in this situation that wouldn't be counted in the 3 choose 2. Uh-huh.
You could pick the same marble.
Right. Okay. When you do the choose notation and you say I have 3 things to choose from and I'm going to pick 2, picking the same one twice is not one of the things that's being counted there, right? So as soon as you say with replacement, you have to cross the choose option off the list. Like you can't set up a choose expression that's going to calculate this correctly. Okay, because it doesn't allow for picking the same things multiple times. So we have to multiply a sequence of probabilities here. Okay, so the chance I pick a red marble first, let's say, would be 1/4, 3/12. And then I have to pick a red again, so that's another 1/4. And then I have to pick a white. What's the chance of that? 7/12. Remember, it doesn't matter, I'm picking it third. All the probabilities are staying the same all the way through this. And then I pick a black marble with a probability of, what's the chance I get a black one? 2/12, 1/6. Okay. All right, then do I just multiply these together? Is that my answer, or do I have to do anything else? I'm not actually done yet. I multiply by something because I can reorganize it. Now, is it 4? Is it 6? How are you guys getting this? What we basically showed here is red, red, white, black,
By 4
right?
factorial.
It would be 4 factorial, except, Anna?
You have 2 reds.
Right, so we got to divide by 2 factorial because there's 2 r's, right? It's like how many ways can you rearrange this? By the rule we just had, it's 4 factorial because there are 4 things, but over 2 factorial because 2 of the 4 things are the same, right? So we should actually be multiplying by, what is that number? 12. Okay? So really, that 12 is going to cancel with this, and I'm going to get 1/4 squared times 7 times 1/6. Does that make sense? Because I canceled this 12 with this 12. Okay. Can somebody give me a decimal for that? 0.0729. And that is the 3 sig fig answer, right? 0.0729. The 0 doesn't count as a sig fig, right? So that's 4 decimal places, but 3 sig figs. Okay? All right, what about the chance that none of the marbles are black? So this time we don't really care about all the different colors. We can divide it into 2 groups, black marbles and non-black marbles, right? What's the chance that I pick a non-black marble on any particular selection? 10/12, 5/6, right? So the chance I get a marble that is not black on any selection is 5/6, but I'm picking 4. It's going to be the same 5/6 to the fourth, right? 5, 6 times 5, 6 times 5, 6 times 5, 6. Now, do I have to worry about order here? No, why not?
Because they're all not block.
Right, it's like how many ways can you rearrange that? Right, there's only one order. So 5, 6 to the fourth, that is your answer. Does that make sense? Okay. Now, I'm gonna ask the same questions, but switch to without replacement. So without replacement, we're back to dependent events. Right? This means as I make selections, the probabilities are going to be changed from one event to the next. That's what dependent events is, right? One event happens, you pick a marble, whatever outcome that is, whether I get a red, a white, or a black marble. When I pick my second marble, the probabilities of each of those outcomes is now different because one of those marbles was taken out. So when one event's occurrence changes how likely other events are to happen, that's when you have dependent events. Okay? So this brings back, we could do this again, right? Except we wouldn't be using these fractions this time. Or now that we're not putting things back, we could do the choose way also. So since we did the multiplying by fractions last time because we had to, let's do these two with the choose notation. What would be my denominator in the first one? 12 choose 4. Okay. And on the top is, I need to count how many ways what I want to happen can happen. I have to pick 2 red. How many ways are there to do that? 3 choose 2. What is 3 choose 2, by the way? Remember that would be like 3 factorial over 2 factorial, 1 factorial. If you cancel everything you can, what's left? 3. That should make sense, right? There's 3 ways to pick 2 marbles out of a set of 3 because you're going to leave 1 marble out each time. And there's 3 different marbles you could leave out. So 3 choose 2 is 3. Then I only have to pick 1 white and I have 7 to pick from. So 7 choose 1, which is obviously 7. And 1 black out of 2, there's going to be 2 ways to pick that. And does it make sense I'm multiplying all these together? Because I have to pick this and this and this. And we said when you use and, you typically multiply. When you use or, you typically add. Okay? So we should multiply here. This is 3 times 7 times 2. So 42. Is this the 495? Maybe this is 495. 12 choose 4. Can someone crunch that? I know there's a 495 in these slides somewhere.
Yeah.
Is that it? Okay. Okay, so this is like a little under 10%, right? Okay, and then the none are black. Can we do the same thing? Would our denominator still be 12 choose 4 here? Is there still 12 choose 4 ways total of things that can happen? Yes, because we're picking 4. But what could I do on the top? I think we can do it with just one choose expression. Right? 10 choose 4. You have to pick from the non-black set, there's 10 of those. It doesn't matter that some of them are red and some of them are white, but you're picking 4 of those 10. So 10 choose 4 over 12 choose 4. What's 10 choose 4? Ten, 9, 8, 7 over 24. How much? 210? 210 over 495. Right? Everybody okay with that? Okay. All right, I'm going to show you another example that is pretty common on the IB exam. In fact, this one came from an IB exam. IB loves to give you these probability problems where there's like zero context. You just have like these abstract events. They say you have these 2 events, A and B, and all we know is the chance of A happening is 0.3 and the chance of B happening is 0.4. And then they ask you a series of questions related to those events based on formulas that we know and information that they gave. A lot of times, I think it's helpful with these kind of problems to use diagrams to solve them. You'll see in a lot of these probability problems, we can use Venn diagrams or tree diagrams. We're going to focus a little more on tree diagrams tomorrow, but I'll show you how I use Venn diagrams. There's a couple different ways you can use Venn diagrams here, but I'll show you one of them today, where you have like your universal set, that's like your sample space, and then we have events A and B occurring in here. Now, in the first part, it says A and B are mutually exclusive. That's a term we went over on Monday. What does that mean? What's that? No overlap, right. There's no chance that A and B happen together. So there are no outcomes where A happens and also B happens. So it would have to look something like this. So this one is easy to label then. You can label Venn diagrams with probability problems where you label the probabilities, and then we would say like the total probability in this box, like the chance of anything at all happening is 1, and we can subdivide that 1 into the different regions, right? So probability of A is 0.3, so 30% of the probability is in that ring, and 40% of it is over here. And if the total of it is 100%, and I have 30% in A and 40% in B, then how much is left in the box that's not in either of those rings? There's 0.3 there, okay? We don't actually need that 0.3 in this problem, but we could label it if we needed to. So it's asking to find the probability of A or B. Now we had a formula on Monday, and this formula is in your packet, that says probability of A or B is in general probability of A plus probability of B, and then you're supposed to subtract the probability of A and B because you double counted that part, right? But in mutually exclusive events, there is no probability of A and B, so we can ignore that part. So all you have to do to get the probability of A or B is add the two probabilities together. So we know this answer is just 0.7, yeah. Okay? But in the second part, they said instead of A and B being mutually exclusive, A and B are independent. Do you remember on Monday in the notes I was talking about how people often confuse those two terms? I think that's why IB set up this question this way. They were testing to see, do people know the difference between mutually exclusive and independent? So mutually exclusive is the one where you have the disjoint sets like that, like there's no overlapping. In independent events, you could have overlap. You would actually. You'll have overlap anytime they're not mutually exclusive. And independent events are never mutually exclusive. So we'll have a picture that looks something like this. Okay, and this time it's a little trickier to label because the 0.3 here is split. Part of it could be in the A only, and part of it could be in the overlap. And same thing for the 0.4. Some of it could go here, and some of it could go there. So we have to figure out how to label the regions. There is, because A and B are independent, we had a formula for the probability of A and B. I gave you like a general formula for A and B, but I said when they're independent, it gets even simpler. Do you remember what you can do for probability of A and B only when they're independent? You just multiply the probabilities together. So it's the probability of A times the probability of B, and since we were given both of those, probability of A times probability of B is just 0.12. Okay, so here I'm going to put 0.12. And knowing how much is in the overlap lets me label the other two regions that include parts of A or B, right? If chance of A happening at all is 0.3, but 0.12 of that is already accounted for, how much is left over here for the chance that only A happens out of A and B? 0.18. So this goes here. And then you can do the same thing for what's the chance that just B happens? 0.28. Okay? And then the probability of A or B, that's what we're being asked to find. Okay, where is A or B in the diagram? This is A and B, right? What represents A or B? That's the exclusive or. So that, remember we said when you use or in English, sometimes that's what you mean, like just one or the other but not both. But in probability, the or is always inclusive. So when you say A or B, you mean at least one of A or B happens. But if they both happen, you should still count it. So it should be all three of these is A or B. 0.58? Yeah, okay. 0.18 plus 0.12, that is the 0.3 we had here, plus 0.28, right? So it would be equal to 0.18 plus 0.12 plus 0.28. And that's going to give us 0.58. The way you could do it, like we actually have enough to use the formula from the packet, right? We could do A plus B, that's 0.7, but then we'd have to subtract the 0.12 that got double counted. If we took 0.7 minus 0.12, we would also get the 0.58. Does that make sense? But having the diagram there makes it easy for you to see which parts you're supposed to be considering. Okay, then they asked one more question, and this is going to lead to something we're going to talk about more tomorrow. So this is a third scenario. It doesn't follow from either of these. Here it says probability of A or B is 0.6. Now remember, they asked you to find A or B up here, and in the mutually exclusive case, A or B was 0.7. In the independent case, A or B came out to 0.58. This is neither of those. So this is a third scenario. They're not mutually exclusive, they're not independent, because probability of A or B came out to 0.6. It's asking you for a different probability this time. What is the one that it's asking you for here? How do you read that? A given B, okay? So I would still want to label the diagram. Okay, let's call this A and this B, okay? Now A or B is 0.6, but A or B encompasses all three of these regions. So that 0.6 is spread somehow over there, but I don't know how to spread it yet, okay? We know A, just A is 0.3, but that's two regions. And B is 0.4, but that's also two regions. Do you see any way to label just, like we have a total of 4 regions here, right? There's A only, A and B, B only, and then there's neither A or B. Do you see any way that you could get one of those? Actually, we could do one really quickly right now, but it's not going to turn out to help us. What's the one we can do just right away?
0.4.
Where does the 0.4 go?
Neither or.
Yeah. Okay, but it turns out that one we don't need. Okay, can we do something else, maybe?
You could find the one in the middle.
Yeah, how do you do it?
You do A plus B.
Uh-huh.
A
So if I
and
add those, that's 0.7.
Yeah, 0.7 minus 0.6.
Right. If you add these, you get more than A or B. Why would you get more than A or B when you add these? Because the overlap has been counted twice. So if you get more than A or B when you add A and B, the amount you're over by is the overlap, because that's the stuff that got double counted. Does that make sense? So if we add these and we get 0.7, but we're only supposed to get 0.6 for the total of all three of these, then 0.1 is in the middle because that got counted twice. Does that make sense? Now that you have the middle, you can easily get the other two, right? What's the A only part? 0.2, because all of A has to be 0.3. And how much is in B only? 0.3. Okay, now we have the whole picture labeled. You could answer any question about events from this. They want A given B. Okay, we're going to talk about conditional probability more tomorrow. But when you're told A given B, that means that you know B already happened, right? So you're not looking at the whole box anymore as your like total sample space. Your sample space now has been stripped away to just the stuff that includes B happening. So in your denominator now, instead of a 1, like 100%, how much of the probability in there corresponds to B having happened? 0.4. So that's your denominator. And just looking at that 0.4, in what part of that did A happen? The 0.1. So that's your numerator. So A given B is 0.1 over 0.4, which is just 1/4. Okay? Make sense?
Yeah.
We're going to talk about conditional probability like a lot of the rest of the week. Okay? Tomorrow we'll do some more problems that use the idea of conditional probability, and then on Friday we're doing something called Bayes' theorem, which is a way to figure out conditional probability in certain situations. Okay? Okay. So we can stop there.